Let's now look at combinations. So the difference between a combination and a permutation. The permutation, the actual order that we arrange things in, that was important. Whereas with a combination, we don't actually care. So it's more a selection of objects rather than an arrangement of objects. So let's see if we can come up with a pattern. So we're going to arrange objects in the line, but this time the order is not important. Then as far as we're concerned, AB, whilst visually it's different to BA, we think of them as the same thing because it's the same objects. So we'll start with this. We've got 5 objects. We're going to arrange 2 of them. Now, if the arrangement was important, we'd have all of these possibilities there. And that we could work out 5p2, there's actually 20 of them. If the order is not important, well, let's cross out the ones that are now doubled up. I can cross all those out, and I'm left with, how many am I left with? 10. But it's not just 10. It's 20 divided by 2 factorial. So it's dividing out the number of ways we could have arranged the objects. So I'm not interested in the way we could arrange them. Each of those pairs I could have arranged 2 factorial ways, but I'm not interested in that. So it's like they're the same thing. So I divide by that number of ways and I get 10. Let's try another one. 5 objects, going to arrange 3 of them. There's a lot of them. There's 60 there. All right, ready? We're going to cross out the double ones. So all the double ups have been crossed out and we've been left with 10, which turns out to be 60 divided by 3 factorial. So again, divided by the number of ways we could have arranged the 3 objects. So there seems to be a clear pattern. So all right, if we have n different objects, we're going to arrange k of them, and we're not worried about the order. So it appears that it's the number of permutations divided by k factorial, the number of ways we could arrange those. That means, because if you remember the formula for npk was n factorial on n minus k factorial. But now we're also going to have a k factorial. Interesting thing about the 2 numbers on the bottom, they add to give n. So they always add to give the number on top. And we have a notation for that. C for combination. And you'll find that, I think, on the division key on your calculator. On most of them. So all right. How many ways can 6 numbers be chosen from 45 numbers, which is the basis of lotto? Yeah, that game where they drop the balls and hopefully people want to win a lot of money. So how many different ways, because they don't care, by the way, in lotto, about the order the balls come out. You just got to get the 6 correct numbers. So it'll be 45C6. Turns out to be 8,145,060. So if you had a lot of patience and a lot of ink, theoretically, you could fill out 8,145,060 entries and guarantee that you'll win lotto. There's a little problem there. It costs 70 cents a game. So it would cost you 5,701,000 in order to do it. Tempting, but remember, you've got to have the $5.7 million first. Because here's the thing. It's still a gamble. But see, the problem is, yes, you're guaranteed to win it. But remember the other rule? If more than one person gets it, you share the money. So now you're gambling that no one else gets that combination. We're going to choose a committee. Our committee has 5 people. And we're choosing them from 7 men, 4 women. How many committees are possible? No restrictions. So again, no restrictions. We don't care about the gender. So there's 11 people, and we're going to choose 5. It's a combination because the order we pick them, we don't care. We just want to get 5 people to go on the committee. 462 it turns out to be. What about if the committee, we're back in the dark ages now, and we say, no, there can only be men on this committee. So now we're only choosing from the 7 men, and we narrow it down quite a bit. Now there's only 21 possible committees. But then Enlightenment comes along, and they say, hang on a sec, this isn't fair. You've got to have at least one woman on your committee. Complementary event idea. Because we've just worked out how many there are all up, how many that contain only males, so the difference must be the ones that contain at least one. Let's say 441. A lot of card games involve this sort of thing. So you deal out 5 cards, and whatever the game you're playing. How many different ways could you be dealt? 5 cards. So there's 52 cards in our pack. 5, because the order that you're dealt the cards, if you are a polite card player, doesn't matter, because you're not meant to pick up your hand until it's completely dealt. So the order they gave the cards doesn't matter. That's how many? 2,598,960 different hands. Now, I don't know how many of you are familiar with different sort of card games, but one of the ones involves 3 of a kind. So 3 of the same number. First thing we have to choose is, when we say 3 of a kind, of what kind? Is it going to be 3 aces, 3 twos, 3 threes, 3 fours, or so on? So there's 13 different, well, we'll call them numbers, even though Jack, Queen, King are not a number, but 13 different numbers we could have. We're going to choose one of them to be 3 of a kind. So that's 13C1, but now there's 4 of them in the pack. I want to choose 3 of them, so 4C3. But I still need to get another 2 cards. So of the 48 cards that are left, now hang on a sec, 48? I've only dealt 3 cards. Isn't there 49 left? Why 48 and not 49? Exactly. So even though I've dealt the 3 of the, well, let's say it was aces. Even though I've dealt the 3 aces, I don't want to give them the other ace, because then they don't have 3 of a kind, they would have 4 of a kind. So there's actually only 48 cards that they can choose from. So 48C2, there we are, 58,656. And so then the probability of getting 3 of a kind, 94 on 2,915. Now for a poker player, that's not actually entirely correct, because I should have also discounted the chance that the other 2 cards were a pair. Because if the other 2 are a pair, I no longer have 3 of a kind, I have a full house. But don't worry, you don't need to know all those terminologies, okay? They cannot ask you a question on something like that without defining all the different rules. About 3% by the way for that. All right, let's look at something from an HSC. We're going to pick a 4-person team. It's chosen at random from 9 women, 7 men. So very similar to our committee question. How many ways can this be done? Right, 16 people all up, so 16C4. Once again, gender doesn't matter here. 1,820. Second part. Well then, what's the probability that the team consists of 4 women? I think it's very similar to our other example. Well now, we're only choosing from the 9. So 9C4, then the probability then, how many ways can it happen? 126 over total number of possibilities, 1,820, 9 and 130. Dividing things up into groups. So, show you this. I'm going to go through a couple of cases here. If we've got m plus n objects, and I'm going to divide it into 2 groups, one group of m, one group of n. How many ways can I do it? M plus n is the number of objects we have, and I'm going to choose m. Now, as soon as I've chosen m, I've automatically created the other group, so I don't have to do anything else. It's automatically got there. You can simplify this a bit, because that's m plus n factorial on m factorial n factorial. So another way of thinking about that is, hang on, what have I got? Total number of arrangements divided by the arrangements within the group. I'm not actually interested in how many arrangements there are, I'm only interested in the group. So I divide out the number of arrangements of each group. Now what happens though in case 2? If I'm dividing a group of 2m objects, but there's 2 groups both of m, I also have to divide it by 2 factorial. We have to divide by the number of ways the groups of the same size can be arranged. And here's the reason why. Where's 2 tables with the same number of people? 10 people. I'm going to divide them into 2 groups of 5. So one way I could have done it, I'll pick these 5 people. You automatically become the other group. That's one way I could have done it. But I could have done it as, I'll pick these 5 people. You automatically become the other group. Different ways of doing it, but remember the order's not important. I still end up with the same 2 groups. So if the group sizes are the same, I divide by the number of ways you can arrange that group, unless you're actually going to do something with the groups. See, if I was to say, well, one group, you're going to go and sit in that corner, and the other group, you're going to sit in that corner, Now I don't divide by the 2 factorial because that would be different to if I sent you to that corner and you to that corner. But if all you're doing is picking the groups, you divide by the number. So 2m factorial. Each of them were of size m, so m factorial, but then divide by the number of ways I could have arranged the number of groups. Let's take it a step further. So I now have m plus n plus p objects all up. And we're going to break them up into a group containing m, then n, then p objects. So what I would have done is this. Well, first of all, I'm going to pick the group with m in it. So from the m plus n plus p objects, I'm going to choose m of them. But now I'm left with n plus p objects. So of that n plus p, I'm going to choose a group of n. And that will then leave me with the third group of p objects. If I play around with the factorials, eventually it becomes this. And so actually it's still the same idea. Because look what ends up on the top of the fraction. On the top of the fraction is the number of ways of arranging all of the objects, and on the bottom it's still just the number of ways I could have arranged the objects in each individual group. Doesn't matter if it's 2 groups, 3 groups, 4 groups, 5 groups, I can still use the same idea. So 15 students are going to be divided into 3 equal groups. It will end up being 15 factorial on 5 factorial, 5 factorial, 5 factorial, 3 factorial. We're also dividing by 3 factorial because the 3 groups are the same size. So the number of ways I could arrange the 3 groups. What's that turn out to be? Oh, look at that nice number. 126, 126. A restaurant has 3 tables. Each of the tables has 4 seats. 12 people arrive for dinner. How many ways can I assign them to the tables? So in other words, I'm going to get these 12 people and put them into 3 groups of 4. 12 factorial of 4 factorial, 4 factorial, 4 factorial, 3 factorial. So I'll divide the patrons into 3 groups. And this is what I was saying. Times another 3 factorial. So in effect, I don't need the 3 factorial on the bottom this time because I'm doing something with the group. I'm saying, oh, you first group, you're going to table 1. Second group, you're going to table 2. Third group, going to table 3. So because they've been arranged, effectively what I'm doing is that, but reality is I just don't divide by the 3 factorial because that's always going to cancel. Because on the bottom, that first 3 factorial on the bottom is the number of ways I could have arranged the groups, but now I'm saying, oh, but now I want to arrange you. So it's effectively saying, hey, you really shouldn't have divided by the number of ways I'm arranging the groups here. So it's just 12. So what do we need to remember then? If we're going to do something with the groups and they're of same size, then I don't need to then work out the number of ways and divide that. So if they are going to be arranged, there's no need to divide by the number of ways the groups can be arranged. Really, a permutation is a combination. It's sometimes strange that we do permutations first and combinations. I mean, I can see why we do, but a permutation is a combination, but it's multiplied by the number of ways the objects can be arranged, and that's effectively what we do with a permutation. So it's another way of thinking about how to do permutations. Sometimes you can say, well, I'm just going to choose the objects, which makes it a combination, but then I'll multiply it by the number of ways I can arrange the objects, and it becomes a permutation. Now, I'm going to show you a couple of ideas that sometimes make problems a little bit easier. A really useful, this what we call the insertion method. Insertion method is when you have a situation where some objects are not allowed to be together, and you would have seen some of those in the questions. So something like this. The letters of the word between, I might have even stolen this out of the textbook. Does it look familiar? The letters of the word between arranged in a line. How many ways can they be arranged if all the E's are separated? So the E's cannot be together. The traditional method. Well, let's work out, because you look after the conditions first. Let's work out how many ways I can place the E's. So there's the spots, and the E's cannot be together. So there's 3 E's. I could put them like that, or I could move that last E to the second last spot, or I could move it to the third last spot. So there are all the ways with the first 2 E's separated by 1 spot. It's 3 ways. Okay. What about if the first 2 E's are separated by 2 spots? Then I could place E second last or last. There's 2 ways I could do it. Well, what happens if I have 3 separating the first 2? Then I could have E at the end, but that's all I could have. So there's 1. All right, but that was when E was in the first spot. What happens if E is not in the first spot and the first 2 E's are separated by 1? Then E could go in the second last or the last. So another 2 spots. Well, what about if the first one's not in the first spot, separated by 2, then there's only one more way I could do it. All right, well, that's if the first 2 E's don't start at the second spot. What happens if the first E is in the third spot? Okay, well, actually, there's only one way I could do that. So I go E, then miss 1 E, then miss 1 E at the end. And I think that's it now, because I can't move the first E any further. So I've come up with 10 ways I can arrange the E's. So then I would say, okay, 10 ways I could arrange the E's, times 4 factorial, let's arrange the other letters. 240 ways. That was a lot of work doing it that way. The insertion method allows us to do this. We think about it a different way. We say, well, instead of looking after the thing with the restriction first, let's look after the thing without the restriction first. And then once they're sorted, then I'll find spots to put the E's in. So there's the remaining letters, B, T, W, and N. There's 4 factorial ways I could arrange them. Let's pretend this is what we've ended up with, B, T, W, and N. The reason I put a space in is what I'm saying is the E's have to go in those spaces. But only 1 E can go in a space, because otherwise I'll then have 2 E's next to each other. So I'm saying, how many spaces have I got? Yes, 5, because I could use a space at the left of B and on the right of N. Of those 5 spaces, I'm going to select 3 of them. I've got to place the E's, times 5C3. What do you know? That's 240. Now that's a heck of a lot quicker than trying to work out all the actual spaces where the E's can go. So I arrange the B, T, W, and N, and then go, righto, I've got to put the E's in. Now, how many ways? Well, then you've got to fill the gaps. Exactly 2 of the E's are together. Okay. Well, again, I'll start with the B, T, W, and N, 4 factorial ways. Exactly 2 of them are together. So now it's like I'm placing 2 objects. A double E and a single E. So they're 2 different things. But I've still only got 5 spaces that I can use. P2 this time, because the order's important now. Because if I place the EE in the first space and then the E in the second space, that would be different to if I place the E in the first place and the EE in the second place. So it'll be times 5 P2. And that comes up to be 480. So it's just an idea that can be useful. Another useful idea, separators. This is good when you have to divide big groups into smaller groups. 3 pirates. Oh, I love a pirate. They're sharing out the contents of a treasure chest. That's how the pirate would say, treasure chest. Containing 48 gold coins. Oh, sorry, I can't help myself. And 2 lead coins. So the treasure chest has 48 gold coins and 2 lead coins. The first pirate takes out coins. So they're sharing up their treasure. And they say, these are the rules. Here's the treasure chest. I'm the captain. I'm going to go last. So you can go first. And you can just keep taking coins out until you get a lead coin. And once you get a lead coin, that's it. That's how much treasure you're getting. So if I'm incredibly unlucky, the first coin pulled out is lead. No, bad luck, I don't get anything. But if I'm real lucky, I'll pull out the 48 gold ones until I hit a lead one, I get all of it. So that's the deal. Once the first pirate gets the lead one, second pirate's turn. Right, your turn. Keep pulling them out until you hit a lead coin, and then whatever's left, the captain's going to take. The third pirate's going to take. So how many ways can these coins be distributed? Think of them as letters rather than coins, because it's no different to saying, how many ways could I arrange the letters, and there's 2 L's and 48 G's. It'd make a very strange word, but it is no different. We're just arranging these letters, L for lead, 48 for gold. So the L's, if you like, are these separators of the 3 pirates. It tells when the next one's going to start. Well, we saw that sort of problem. If we wanted to make words, we said, 50 factorial divided by the repetitions. So 2 L's, 2 factorial, 48 G's, 48 factorial. We end up with 1,225 ways of doing that. Here's one that was in the actual HSC, extension 2 HSC. It's a similar one. How many ways can 10 identical coins be allocated to 4 different boxes? But it's the same idea. If I say, well, no, actually, I haven't got 10 coins. I've got 10 gold coins. And how many lead coins would I need to get them into 4 different boxes? I'd need 3. Because the first coin, bang, stop, that box is done. So I'll think of the question as 10 C's for the coins, 3 S's. I'm just calling the S for separator. And 3 S's. But it's exactly the same question as the one before now. How many ways can I arrange the 10 C's and the 3 S's? Well, 13 factorial on 3 factorial, 10 factorial, 286. Like I say, that was an extension 2 probability question. Question 16, which is the last question on the paper, 1%. 1% of the state got that correct. Let's try another one. This one comes from an extension 2 HSC. A hostel has 4 vacant rooms. Each room can accommodate a maximum of 4 people. How many ways can 6 people be accommodated in the 4 rooms? So the first thing I'm doing is total number of ways, no restrictions. If there was no restrictions, then it's 4 to the power of 6. Right? Because there's 4 vacant rooms, but there's 6 people coming along. So the first person's coming along, I've got 4 to choose from. Second person comes along, I've got 4 to choose from. Third person, that's 4 times 4 times 4, 4 to the power of 6. Let's work out the number of ways 6 in a room, because what we're saying is I'm going to actually work out the other situation, the complementary event. I'm going to take away the ones that I can't have. So I've worked out how many in total. I'll take away all the possibilities where all 6 are in the one room, because that wouldn't work for what we want, is it? Because we said each room can accommodate a maximum of 4. So I can't have 6 in a room. How many ways? Well, it'll be 4C1. All I've got to do now is pick the room. Which room are the 6 people going to go into? 4C1. What else can't we? Well, we can't have 5 in a room either. So let's work out 5 in a room. So first of all, we're going to pick the room that has the 5 people, so 4C1. Then I've got to choose which 5 of the 6 are going to go in there. 6C5. That now leaves me with one person who has to go into one of the 3 rooms. Chooses one of the 3 rooms, 3C1, 72. And that should be it, because we're allowed 4 people in a room. So 4,096 minus 4 minus 72, 4,020. The state did a bit better. 15% of the state got that one. Until you realise it was actually a multiple choice question. And so you would think, well, randomly guessing 25%, surely. So they got less than just randomly guessing. So 15% got it right. All right, 14E we will now play with.